Have you ever looked up at the night sky and wondered what secrets it might be whispering to us? The universe is vast beyond comprehension, a silent, sprawling expanse filled with more stars than grains of sand on every beach. Yet every now and then it breaks its silence. Strange, unexplained signals ripple across the cosmos, reaching our telescopes like cosmic Morse code. Some last mere milliseconds, others repeat in patterns we can't decipher. They come from deep space, from places so distant, their light takes millions of years to reach us. These aren't just random blips, they're deliberate, mysterious, and packed with questions we're only beginning to ask. Imagine tuning into a radio frequency and hearing a voice from another world. That's the thrill astronomers feel when they detect these signals. They're called fast radio bursts, gamma-ray flashes, and cosmic whispers, each one a puzzle wrapped in enigma. Some seem to defy the laws of physics, pulsing with energies we can barely fathom. Others repeat in rhythms that hint at intelligence, sparking debates about whether we're alone in the universe. But here's what's truly astonishing. Out of the countless signals the universe sends, 25 stand out as the most baffling. 25 cosmic anomalies that challenge everything we think we know. This isn't just a story about distant stars or cold, empty space. It's about the human hunger to understand the unknown. For centuries, we've searched the skies for answers, decoding the language of light and radio waves. And every time we think we've figured it out, the universe throws us another curveball. Today, we're diving into those curveballs, the 25 most enigmatic signals ever recorded. Some might be natural phenomena, cosmic fireworks from dying stars or colliding black holes. Others, well, that's where things get interesting. So, if you've ever felt that tug of curiosity when you stare up at the stars, you're in the right place. Strap in, we're about to take a journey into the deepest, strangest corners of the cosmos and the signals that just might change how we see it forever. Out of all the strange whispers from the cosmos, one stands out above the rest, a signal so powerful, so bizarre that the scientist who discovered it scrawled, "Wow." In the margin of the data printout, that's how it got its name, the WOW signal. It happened on August 15, 1977, when a radio telescope in Ohio picked up a burst of noise so intense it dwarfed the usual background static of space. For 72 seconds, a narrowband radio signal, a concentrated beam of energy blasted through the void at a frequency scientists had long considered ideal for interstellar communication. And then, just as suddenly as it began, it vanished. This wasn't some faint blip lost in cosmic noise. The signal was 30 times stronger than the surrounding radiation, matching exactly what astronomers predicted an artificial transmission from another civilization might look like. Even stranger, it came from the direction of the Sagittarius constellation, a region packed with stars and possibly planets. For decades, researchers have scoured that patch of sky, listening for a repeat, but the signal never came back. So what was it? The leading natural explanation points to hydrogen clouds or comets. But here's the catch: the WOW signal's frequency doesn't match known comet emissions, and hydrogen doesn't create bursts that intense. Others suggest it might have been a reflected human transmission, bouncing off space debris, but no earthly broadcasts matched its profile. Then, of course, there's the tantalizing possibility: was it a deliberate signal, a cosmic hello from something or someone out there? We may never know for sure, but one thing's certain: after nearly 50 years, the WOW signal remains a mystery, a single, electrifying moment when the universe seemed to shout directly at us and left us wondering what it meant. The WOW signal didn't just fade into static, it ignited a firestorm of curiosity that still burns today. In the decades since that fleeting 72-second burst, astronomers have turned their telescopes toward the same patch of sky over and over, hoping for a repeat performance. Bigger, more sensitive instruments like the Very Large Array and the Allen Telescope Array have scanned the area, listening for even the faintest echo of that original signal. But silence has been the only reply. That absence speaks volumes. If it were a natural phenomenon, why hasn't it happened again? If it were artificial, why wouldn't whoever sent it try to make contact once more? The unanswered questions have turned the WOW signal into more than just a scientific anomaly. It's become a cultural touchstone, a symbol of humanity's longing to connect with the cosmos. This one-off event reshaped how we search for extraterrestrial intelligence. Before 1977, SETI, the search for extraterrestrial intelligence was often dismissed as fringe science, a pursuit more suited to science fiction than serious research. But the WOW signal changed that. It was tangible, it was real data, something scientists could point to and say, this doesn't fit our models. Suddenly, the idea of listening for deliberate signals didn't seem so far-fetched. Funding for SETI projects increased, and the scientific community began treating the search for cosmic neighbors with renewed respect. The WOW signal became the gold standard, the benchmark against which all other unexplained radio bursts are measured. Even now, when a new anomaly pops up, the first question is always, is this another WOW? Yet for all its fame, the WOW signal remains frustratingly unique. Some researchers argue that's precisely what makes it so compelling. Most cosmic phenomena, pulsars, quasars, even supernova, follow predictable patterns or repeat in ways we can study. But the WOW signal defies categorization. It's a cosmic one-hit wonder, a single note in an otherwise silent symphony. That singularity has fueled endless speculation. Could it have been a malfunction? Unlikely. The signal was too clean, too perfectly aligned with the frequency hydrogen absorbs and emits, a logical choice for interstellar messaging. Could it have been a natural event we simply don't understand yet? Possibly. The universe is full of surprises, but the timing, the intensity, and the eerie precision keep bringing us back to that spine-tingling question: what if we weren't alone in that moment? The legacy of the WOW signal isn't just in the data, it's in the way it reshaped our imagination. Books, documentaries, even songs have been written about it. It's inspired generations of scientists to keep scanning the skies, to keep asking, are we listening hard enough? And perhaps most importantly, it's reminded us that the universe is vast, mysterious, and capable of throwing curveballs we can't yet explain. Every unexplained signal that comes after is measured against that one electrifying burst from 1977, a whisper from the cosmos that still echoes in our collective curiosity. While the WOW signal remains a solitary enigma, the universe has another, even more persistent mystery up its sleeve: fast radio bursts. These are not fleeting whispers but violent, millisecond-long screams of energy, each one packing more power than the sun emits in decades. First detected in 2007, FRBs erupt from galaxies billions of light-years away, arriving at Earth as blips so brief you could blink and miss them. Yet in that fraction of a second, they outshine entire galaxies. The strangest part, most burst once and vanish, leaving astronomers scrambling to catch them before they disappear forever. But a few defy expectations. Take FRB 121102, the first known repeater. Unlike its one-and-done cousins, this signal from a dwarf galaxy 3 billion light-years away sends out bursts in erratic, unpredictable patterns. Sometimes it's silent for months, then suddenly erupts in a flurry of activity. That repetition is what makes it so tantalizing. Natural cosmic events like neutron stars colliding don't usually repeat. But this does. So what could possibly generate such staggering energy over and over? Highly magnetized neutron stars are the leading suspects. When their crusts crack under immense pressure, they might unleash bursts of radiation powerful enough to reach across the universe. But there's a catch. Some FRBs emit energy levels that push the limits of what even magnetars should produce. That discrepancy has opened the door to wilder theories, from cosmic strings to, yes, alien technology. Imagine a civilization harnessing the energy of stars to power interstellar beacons or propulsion systems. Those bursts could be the cosmic equivalent of a lighthouse beam sweeping past Earth. Of course, extraordinary claims require extraordinary evidence, and so far, nature still holds the winning cards. But every new detection adds another piece to the puzzle. In 2020, astronomers traced an FRB to our own galactic backyard, a magnetar just 30,000 light-years away. While this confirmed magnetars could produce some bursts, others, like 121102, remain stubbornly unexplained. The universe, it seems, loves keeping secrets. Each FRB is a breadcrumb trail leading us deeper into the cosmic unknown, challenging us to rethink what's possible. And with every strange, repeating signal, one question lingers. Are we listening to the death throes of dying stars, or the first faint whispers of something far more profound? The repeating fast radio bursts aren't just cosmic oddities. They're revolutionizing how we understand the universe. While most FRBs flash once and fade into oblivion, these stubborn repeaters throw predictability out the window. Take FRB 181214, for example. Discovered in 2018, it cycles through periods of frenzied activity, firing off dozens of bursts in a single day, then falls silent for months like it's taunting us. This isn't just random noise, it's a pattern that defies the laws of cosmic chaos, and that's what makes them so maddening and exhilarating for scientists. For decades, astronomers assumed all FRBs were one-off catastrophes, neutron stars colliding, black holes swallowing matter, or other violent, unrepeatable events. But the discovery of repeating bursts shattered that assumption. Suddenly, the rulebook had to be rewritten. Why do some repeat while others don't? What cosmic engine could possibly reboot itself with such erratic precision? The leading theory magnetars fit some of the data, but not all of it. These ultra-dense, spinning stellar corpses, bristling with magnetic fields trillions of times stronger than Earth's, can indeed unleash bursts when their crusts fracture under strain. But here's the catch: some repeating FRBs emit energy so extreme, they'd require magnetars to behave in ways we've never observed. It's like discovering a car that occasionally turns into a rocket, possible in theory, but where's the engine? That gap in understanding has led to some breathtaking breakthroughs. In 2022, astronomers pinpointed a repeating FRB to a globular cluster, a dense swarm of ancient stars not typically associated with magnetars. This raised eyebrows. Could there be an entirely new class of objects lurking in these cosmic crowds? Then, in 2023, another repeater was traced to a galaxy with extreme magnetic activity, suggesting environments we've barely begun to study might be breeding these signals. Each discovery peels back another layer, revealing just how little we know about the forces shaping the cosmos. Yet for all the progress, every answer seems to spawn three new questions. Take the case of FRB 190523, a repeater that not only pulses unpredictably but also shows a bizarre, drifting pattern. Its signal frequency slides downward over time like a cosmic trombone. No known natural phenomenon fully explains this. Some researchers have even floated the idea of artificial origins, not necessarily aliens, but perhaps advanced astrophysical processes we haven't imagined yet. After all, pulsars were once mistaken for extraterrestrial beacons before we understood neutron stars. Could repeating FRBs be the next great cosmic misunderstanding? What's clear is this: these signals are forcing us to rethink the boundaries of physics. They're not just blips in the data, they're windows into the universe's most extreme environments. With every new detection, telescopes grow more sensitive, algorithms get sharper, and the chances of cracking the code increase. One day, we might look back at this era as the turning point, when the universe stopped whispering and started speaking in a language we finally learned to hear. Until then, the repeating FRBs continue their cryptic transmissions, daring us to listen closer. Long before fast radio bursts became astronomy's hottest mystery, there was one that slipped past everyone: the Oumuamua burst. It happened in 2001, buried in archived data from the Parkes Radio Telescope in Australia. Astronomer Duncan Oumuamua and his student David Narkevic weren't even looking for cosmic anomalies that day. They were sifting through old observations of the Magellanic Clouds, searching for pulsars. What they stumbled upon was something far stranger: a single, blistering burst of radio waves lasting just 5 milliseconds. 5 milliseconds shorter than a camera flash, but in that blink of cosmic time, it unleashed as much energy as the sun does in a month. At first, skepticism ran high. Could this just be terrestrial interference, a passing satellite, a rogue microwave oven, or some glitch in the system? After all, Parkes had a history of picking up human-made noise. But the Oumuamua burst was different. It came with a telltale fingerprint called dispersion, a spreading out of radio waves caused by traveling through interstellar gas. The farther a signal travels, the more it disperses. This one was so stretched it had to have come from far beyond our galaxy. The implications were staggering. This wasn't just a local hiccup. It was a scream from the distant universe, a flash so bright it pierced through cosmic fog like a lighthouse beam cutting through mist. Yet for years, the scientific community hesitated. Without a second burst to compare it to, the Oumuamua burst languished as a curiosity, an outlier that might never be explained. Then, in 2007, another burst lit up the data. Then another. Suddenly, it was clear Oumuamua hadn't found a fluke. He discovered the first glimpse of an entirely new cosmic phenomenon. Today, we know these as fast radio bursts, but back then they were ghosts in the machine, so fleeting, so unpredictable that some researchers wondered if they'd ever be understood. What makes the Oumuamua burst special isn't just its serendipitous discovery. It's the blueprint it provided. That single burst taught astronomers what to look for: the sharp spike of energy, the telltale dispersion, the absence of any obvious source. It set the stage for every FRB detected since. But here's the twist: even now, decades later, we still don't know exactly what caused it. Magnetars colliding neutron stars. Something more exotic. The Oumuamua burst refuses to give up its secrets. It remains the original cosmic cipher, a 5-millisecond enigma that rewrote the rules and left us staring at the sky, hungry for answers. In the summer of 2020, astronomers at the Breakthrough Listen project caught something extraordinary: a slender, steady radio signal at 982 MHz, humming from the direction of Proxima Centauri, the closest star system to our Sun. Dubbed BLC-1, this narrowband transmission sent shockwaves through the scientific community. Unlike the chaotic bursts of natural cosmic noise, this signal was clean, concentrated, and eerily reminiscent of the kind of deliberate radio emission a technological civilization might produce. For a brief, electrifying moment, it felt like we might have stumbled onto the real deal, the first concrete whisper of intelligence beyond Earth. The excitement wasn't just about the signal itself, but where it came from. Proxima Centauri isn't just any star. It's a red dwarf with at least 2 known planets, one of which orbits in the habitable zone, where liquid water and maybe life could exist. The idea that a signal could originate from right next door, cosmically speaking, was staggering. Teams scrambled to verify the finding, ruling out satellites, aircraft, and ground-based interference. The signal even exhibited a subtle drift in frequency, the kind you'd expect from a transmitter on a moving planet. The pieces seemed to fit until they didn't. Months of painstaking analysis revealed the sobering truth. BLC-1 wasn't a message from another world. It was almost certainly human-made interference, likely a rogue radio signal bouncing off a satellite or even a malfunctioning electronic device on Earth. The telltale clue: further observations detected similar signals at other frequencies, something natural cosmic emissions wouldn't produce. The dream of first contact faded, but the aftermath left behind something just as valuable: a masterclass in scientific caution. What made BLC-1 different from past false alarms was the rigor of its investigation. Unlike the WOW signal, which was spotted retroactively in data, this detection was part of a systematic search. Every step, from initial identification to eventual debunking, was documented transparently, showing the world how proper SETI research unfolds. Scientists didn't jump to sensational conclusions. They followed the evidence even when it led to disappointment. That process, though less glamorous than headlines about aliens, is the bedrock of credible science. The legacy of BLC-1 isn't just a lesson in humility, it's a roadmap for the future. As our telescopes grow more sensitive, we'll inevitably catch more signals that almost fit the bill. Some might even be harder to dismiss. The challenge isn't just finding a needle in the cosmic haystack, but knowing how to examine it without assuming it's gold. Proxima Centauri's false alarm taught us that the search for extraterrestrial intelligence isn't a sprint to discovery, but a marathon of patience, skepticism, and meticulous verification. And somewhere out there, amidst the noise, the real signal might still be waiting. Some stars flicker like distant candles in the wind, but none behave quite like KIC 8462852, better known as Tabby's star. Nestled in the Cygnus constellation, this unassuming flicker of light became one of the most talked about cosmic mysteries when astronomers noticed something impossible. It was dimming erratically, as if something massive and unseen kept passing in front of it. Most stars with planets dim in predictable, rhythmic patterns like clockwork shadows cast by orbiting worlds. But Tabby's star, its light dips were chaotic, with brightness drops as steep as 22%, far too extreme for any known planet. The first hints of strangeness came from NASA's Kepler Space Telescope, which caught the star undergoing bizarre, asymmetrical dimming events between 2009 and 2013. Some dips lasted days, others stretched for weeks, and none followed a pattern. The data looked less like a star with planets and more like something out of science fiction. That's when the wild theories took off. Could this be evidence of an alien megastructure, a Dyson swarm perhaps? Imagine a civilization so advanced it builds massive solar collectors around its star to harness energy. Such a structure would block light unevenly, exactly like what Kepler observed. But before we jump to cosmic construction sites, there's another, less sensational explanation: dust. Years of follow-up observations revealed that the star's light dims more at certain wavelengths, a signature that points to fine particles, maybe from comets, asteroids, or even a colossal planetary collision. The problem: even dust doesn't fully explain the star's extreme behavior. In 2018, Tabby's star dimmed again, abruptly and dramatically, reigniting the debate. This time, telescopes caught the event in real time, and the data painted a messy picture. The dimming wasn't uniform. It was patchy, as if whatever blocked the light wasn't a single solid object but a chaotic, evolving cloud. So where does that leave us? The megastructure idea still lingers on the fringes, but most astronomers lean toward natural causes, just not any we've seen before. One leading theory suggests the star is devouring a planet, its gravity tearing the world apart into swirling debris that occasionally eclipses its light. Another proposes a massive ringed planet like Saturn on steroids, with uneven rings casting weird shadows. Then there's the possibility of internal stellar activity, though no known type of star behaves this way. Tabby's star refuses to fit neatly into any box. It's a cosmic Rorschach test, revealing more about our curiosity than its own secrets. Every new observation adds layers to the mystery, challenging us to rethink what's possible. Whether it's dust, planets, or something far stranger, one thing's certain: this star has rewritten the rules, and astronomers are still scrambling to catch up. The universe, it seems, has a flair for the dramatic, and Tabby's star is its latest, greatest performance. In 2015, a radio telescope in Russia picked up something unusual, a strong, narrowband signal from a star strikingly similar to our own Sun. Located 94 light-years away in the constellation Hercules, HD 164595 wasn't just any star. It was a near twin of the Sun, slightly older and metal-rich, with at least one known Neptune-like planet. And for a single, tantalizing moment, it seemed to be shouting in our direction. The signal, detected by the Rattan 600 telescope, blipped at 11 GHz, a frequency with no known natural explanation. Even more intriguing, if this was a deliberate broadcast, the energy required would eclipse Earth's total power output by a factor of billions. The implications were staggering. Were we hearing an alien civilization's equivalent of a cosmic flare gun? The discovery sent ripples through the scientific community. SETI researchers quickly trained the Allen telescope array on the star, hoping for a repeat. News outlets buzzed with speculation, but within weeks the excitement fizzled. Further analysis revealed the signal's fatal flaw: it never reappeared. In the world of cosmic detective work, one-off detections are red flags. Real astronomical signals, especially those hinting at intelligence, tend to persist or repeat. This one didn't. The leading theory, a passing satellite or military transmission, bouncing off debris or atmospheric layers, masquerading as something far more exotic. Even the telescope's own quirks couldn't be ruled out. Rattan 600's unique design made it prone to picking up terrestrial interference. Yet the HD 164595 signal wasn't just a false alarm. It was a crash course in the messy reality of hunting for extraterrestrial whispers. Unlike the WOW signal, which came from an era with fewer human-made radio sources, this detection happened in a world saturated with noise. Satellites, radar, even microwave ovens can mimic the hallmarks of an alien broadcast. Distinguishing cosmic gold from earthly static requires more than just a sharp telescope. It demands relentless scrutiny. Every candidate signal must pass brutal tests. Does it repeat? Does it match known natural phenomena? Could it be human-made? Most, like this one, crumble under the weight of scrutiny. What makes this signal special isn't what it turned out to be, but what it represents, the needle in a haystack challenge of modern SETI. For every genuine cosmic mystery, there are thousands of false leads, yet each one tightens the protocols, sharpening our ability to spot the real deal. HD 164595 may have been a cosmic mirage, but it's also a reminder. The universe is vast, and somewhere in the noise, a real signal might still be waiting. And when it comes, we'll be ready, not because we've found answers, but because we've learned how to ask better questions. In the early 2000s, a signal unlike any other quietly slipped into the data streams of the SETI at Home project, a faint, repeating whisper from deep space that would become known as SHB-02+14a. Detected in 2003, this wasn't a one-off blast like the WOW signal or a millisecond scream like fast radio bursts. It was something far subtler, a signal that reappeared 3 times, hovering eerily close to 1420 MHz, the frequency of hydrogen, the most abundant element in the universe and a logical choice for any civilization trying to be heard. What made SHB-02+14 so compelling wasn't just its repetition, but its location. It seemed to originate from a point between the constellations Pisces and Aries, where no known stars or planets stood out. There was no obvious source, no pulsar, no quasar, just empty space. And yet there it was, a signal drifting slightly in frequency, as if coming from a planet orbiting a distant star. The drift matched what you'd expect from a transmitter on a moving world, adding another layer of intrigue. Skeptics were quick to offer natural explanations. Could it be interference from Earth? Unlikely. The signal's frequency shift didn't match any known satellites or aircraft. Was it a glitch in the software? SETI at home's distributed computing model meant thousands of users' machines processed the data, making systemic errors improbable. Then there's the cosmic static hypothesis. Perhaps an undetected quasar or a rogue hydrogen cloud emitted the signal. But why would such a source repeat in such a peculiar way? The debate took a sharper turn when astronomers noticed something unsettling. The signal's frequency wasn't just near the hydrogen line, it was too close. Natural cosmic phenomena rarely emit such precise, narrowband signals. This was more like a laser beam than a star's roar. That precision is what keeps the artificial origin theory alive. If a civilization were trying to communicate, targeting hydrogen's frequency would be a clever move, a universal landmark any advanced species would recognize. Yet for all the speculation, SHB-02 plus 14 remains an enigma. Follow-up observations failed to detect it again, leaving scientists with a handful of tantalizing data points and no definitive answers. It's a ghost in the machine, a whisper that teased the boundaries of what might be possible. Whether it was a cosmic fluke, an unimagined natural phenomenon, or something far more profound, one thing's certain. It's a reminder that the universe is still full of voices we've barely begun to understand. And sometimes the faintest signals ask the loudest questions. Picture this: astronomers at Australia's Parkes Observatory, a facility famous for catching the first whispers of fast radio bursts, suddenly detect something bizarre: radio pulses so peculiar they seem to defy physics. Dubbed Puritans, these signals had all the hallmarks of cosmic origins. They arrived from the sky, exhibited the telltale dispersion of distant sources, and even matched the profile of potential extraterrestrial transmissions. There was just one problem: they weren't coming from space at all. The mystery deepened when researchers noticed something odd. These signals only appeared during daylight hours, specifically around lunchtime. Coincidence? Unlikely. The team began to suspect a terrestrial culprit, but tracking it down felt like chasing a ghost. The signals were sporadic, unpredictable, and maddeningly local. Then came the breakthrough. Someone left the observatory's kitchen door open during an experiment. Moments later, a Puritan blipped onto the screens just as a staff member heated up leftovers. The culprit: a microwave oven. Not just any microwave, though. These signals only appeared when the oven door was opened mid-cycle, releasing a burst of radio waves that bounced off the observatory's dish. The universe wasn't whispering, it was someone reheating coffee. The revelation was equal parts hilarious and humbling. Here was a world-class radio telescope capable of detecting emissions billions of light-years away, fooled by a $30 appliance. But the Puritans weren't just a cosmic prank. They became a masterclass in scientific rigor. Before the microwave explanation, astronomers had to rule out atmospheric phenomena, satellite interference, and even secret military tests. Each dead end reinforced a vital lesson. Extraordinary claims demand extraordinary evidence. The ordeal also reshaped how observatories handle local interference, leading to stricter protocols, like keeping kitchen appliances far from sensitive equipment. What's astonishing isn't just the mix-up, but how long it took to solve. Puritans first appeared in data as early as 1998, yet the microwave connection wasn't confirmed until 2015. 17 years of head-scratching, all because no one thought to question the humble kitchen appliance. The tale serves as a reminder: sometimes the universe's greatest mysteries aren't found in distant galaxies, but right under our noses, or in this case, next to the break room. The legacy of the Puritans isn't just a punchline. It's a testament to the messy human side of science. For all our advanced technology and sophisticated theories, progress often hinges on something far simpler: curiosity, persistence, and the willingness to laugh at ourselves. After all, if a microwave can mimic a cosmic phenomenon, what other everyday mysteries might be hiding in plain sight, waiting for someone to open the right door, literally? It was a discovery that sent shockwaves through the scientific community, and for a brief, electrifying moment, made researchers wonder if they'd stumbled onto evidence of extraterrestrial intelligence. In 1967, graduate student Jocelyn Bell Burnell was poring over data from a new radio telescope near Cambridge when she noticed something bizarre. A series of perfectly timed pulses arriving every 1.337 seconds with uncanny precision. The signal was so regular, so artificial seeming, that her team half-jokingly labeled it LGM1, short for Little Green Men. After all, what natural phenomenon could possibly tick with the mechanical rhythm of a cosmic metronome? The pulses defied all expectations. Stars flicker, galaxies hum with static, but nothing in the known universe emitted signals this precise. For weeks, the team wrestled with the possibility they detected a beacon, an interstellar distress call, or perhaps a greeting from a distant civilization. The implications were staggering, but science thrives on skepticism, and soon a more grounded explanation emerged. These weren't alien messages, they were the death throes of an unimaginably dense stellar corpse, a neutron star spinning at dizzying speeds, its magnetic field funneling radio waves into a lighthouse-like beam that swept past Earth with each rotation. The revelation transformed astrophysics overnight. Bell Burnell's scruffy little signal became the first identified pulsar, opening a window into one of the universe's most extreme environments. Neutron stars are the collapsed cores of massive supernova, packing more mass than the Sun into a sphere just 12 miles wide. A teaspoon of their material would weigh billions of tons. Their discovery solved mysteries about stellar evolution, cosmic rays, and even the origins of heavy elements. Yet the real magic lies in their pulses, clocks so precise they rival atomic timekeeping. Astronomers now use them to test Einstein's theories, map the galaxy, and even navigate spacecraft. But the story of LGM1 isn't just about scientific triumph. It's a reminder of how easily the unknown can spark our imagination. Those early months of uncertainty, the thrill of the unexplained, the tension between skepticism and wonder, mirror every great discovery in astronomy. Today, we know of thousands of pulsars, each with its own rhythm, yet none have ever repeated the tantalizing ambiguity of that first signal. The universe, it seems, has a way of keeping us guessing. Just when we think we've decoded its language, it throws us another curveball, like a cosmic inside joke, where the punchline is always deeper than we expect. Tabby's star might be the most famous cosmic oddball, but it's far from alone in its strangeness. Take J1407b, for instance, a planet so bizarre it makes our entire solar system look tame. Orbiting a young sun-like star 434 light-years away, this world isn't just unusual, it's surrounded by a ring system 200 times wider than Saturn's. Imagine rings so vast they stretch farther than the distance between Earth and the Sun, casting shadows so dramatic they dim their host star by a staggering 95%. For comparison, when Jupiter passes in front of our Sun, it blocks barely 1% of the light. J1407b doesn't just eclipse its star, it practically swallows it whole. What could possibly create such a colossal structure? The leading theory points to a newborn gas giant, still gathering material from its primordial disk, with rings so massive they're practically a snapshot of planetary formation in overdrive. But here's where it gets even weirder. Gaps in those rings suggest moons might be forming, carving out paths like cosmic snowplows. It's a dynamic, messy system, nothing like the orderly orbits we're used to. And while it's not an alien megastructure, it challenges our assumptions about how planets evolve. If rings this extreme can exist, what else might be lurking in the unseen corners of star systems? J1407b and Tabby's star represent two sides of the same cosmic coin, one a natural wonder pushing the limits of physics, the other a mystery that still leaves room for the extraordinary. But they're just the tip of the iceberg. Across the galaxy, stars flicker in ways we can't yet explain. There's VVVWIT07, a giant star that dims by 80% at irregular intervals as if something or someone is flicking a celestial light switch. Then there's Epic 249706424, a red dwarf with dips so sharp and symmetrical they look engineered. The diversity of these puzzles is what makes them so thrilling. Some, like J1407b's rings, are likely natural phenomena we've yet to fully understand. Others, like Tabby's star's erratic dimming, hover in the gray area between the known and the unimaginable. And that's the beauty of cosmic mysteries. They don't just test our knowledge, they stretch our imagination. Every odd signal, every flickering star is a question waiting to be answered. Some will turn out to be dust or planets or magnetic storms, but others, well, that's why we keep looking up, because in a universe this vast, the line between science and speculation is always shifting, and the next great discovery might be hiding in the next flicker of light. In October 2017, astronomers spotted something streaking through our solar system that didn't belong, a strange, cigar-shaped object moving too fast to be bound by the sun's gravity. They named it Oumuamua, Hawaiian for scout or messenger from afar, and it became the first confirmed visitor from another star system. But what made Oumuamua unforgettable wasn't just its interstellar origins. It was the way it behaved. As it raced away from the sun, something inexplicable happened. It accelerated as if pushed by an unseen force. Natural explanations piled up quickly. Maybe outgassing, the release of trapped gases, gave it a nudge like a cosmic soda can fizzing in the vacuum. The problem, Oumuamua showed no visible coma or tail, the usual fingerprints of outgassing. Others suggested it might be a hydrogen iceberg sublimating silently in sunlight. But hydrogen ice is fragile, unlikely to survive the journey between stars. The more scientists studied it, the more Oumuamua resisted easy answers. Then came the boldest theory. What if it wasn't natural at all? Harvard astronomer Avi Loeb famously posited that Oumuamua could be artificial, a light sail or probe from another civilization using sunlight for propulsion. The idea ignited fierce debate. Critics argued it was classic sensationalism, reaching for aliens when simpler explanations existed. Yet even skeptical astronomers admitted one thing: Oumuamua's acceleration was unprecedented. Nothing in our solar system, no comet or asteroid, had ever behaved quite like it. Whether alien artifact or cosmic oddball, Oumuamua's legacy is this: it reminded us that the universe is full of surprises. Just when we think we've catalogued every kind of object, something slips through the cracks, defying our models and sparking new questions. It's the same thrill that comes with unexplained signals, those flickers of mystery that keep astronomers awake at night. Because whether it's a distant radio burst or a speeding interstellar visitor, these anomalies share one vital trait: they don't just challenge what we know. They force us to imagine what we don't. In 2016, astronomer Ermanno Bora dropped a bombshell. He claimed to have found not one, but 234 stars behaving in ways no natural phenomenon could explain. Each displayed rapid, rhythmic pulses of light, perfectly spaced at intervals suggesting an artificial origin. The implications were staggering. If true, this wasn't just a potential sign of extraterrestrial intelligence. It was a chorus of civilizations, all seemingly broadcasting the same strange signal. Media outlets erupted with headlines heralding the discovery as humanity's first brush with cosmic neighbors. But within weeks, the excitement crumbled under the weight of sober scientific scrutiny. The first red flag, the signal's uniformity. Nature thrives on chaos. Stars flicker, pulsars spin at unique rates, even fast radio bursts vary in timing and intensity. Yet Bora's stars pulsed with eerie synchronization, all clustered around the same frequency. That level of consistency is vanishingly rare in astronomy, raising immediate skepticism. Then came the statistical fluke. Bora's team had sifted through millions of stars in the Sloan Digital Sky Survey, searching for patterns. In any dataset that large, anomalies are inevitable. Random noise can mimic signals if you look hard enough. Other researchers pointed out that the discovery fit neatly into the expected number of false positives from such a massive search. The universe, it seemed, had played a cruel trick of coincidence. But the real lesson here wasn't about aliens, it was about scientific rigor. Borer's paper, though peer-reviewed, had skipped a critical step, ruling out instrumental errors. Follow-up observations revealed that many of the pulsing stars were artifacts of the telescope's optics, their strange signals born not in distant galaxies but in the quirks of Earth-bound equipment. The episode became a cautionary tale about jumping to conclusions, especially when the stakes and the headlines are so high, yet buried in the backlash was a silver lining. Borer's methods, though flawed, pushed the boundaries of how we search for extraterrestrial technosignatures, traces of advanced technology, like laser pulses or structured radio waves. His work inspired more nuanced approaches, like the Breakthrough Listen Initiative's laser surveys, which now account for false positives with military-grade precision. Science, after all, advances through missteps as much as breakthroughs. Those 234 stars may not have been shouting into the void, but they taught us how to listen better. And in the grand search for cosmic company, that's progress worth celebrating. Among the countless mysteries of the cosmos, few are as perplexing as dark matter, the invisible glue holding galaxies together, making up 85% of the universe's mass, yet refusing to interact with light. We can't see it, touch it, or even detect it directly, but what if some of those unexplained signals from deep space, like fast radio bursts, aren't just astrophysical oddities? What if they're dark matter itself whispering to us this isn't just science fiction? A handful of theoretical physicists have floated a radical idea. Certain FRBs could be the fingerprints of dark matter particles colliding or decaying in ways we don't yet understand. Imagine a WIMP, a weakly interacting massive particle, one of the leading dark matter candidates, annihilating in a distant galaxy, releasing a burst of energy so intense it ripples across the universe as a radio scream. Or picture actions, another theoretical particle, converting into radio waves under the grip of a black hole's magnetic field. These scenarios sound wild, but they're rooted in real math, pushing the boundaries of known physics. The appeal of this hypothesis lies in its audacity. FRBs are already outliers, defying conventional explanations. Their sheer energy, their fleeting nature, their uneven distribution, none of it fits neatly into our current models of neutron stars or magnetars. Dark matter, by definition, is the ultimate outlier. If these two mysteries turned out to be linked, it would rewrite textbooks overnight. But here's the catch: extraordinary claims demand extraordinary evidence, and so far, the dark matter radio theory is more tantalizing than proven. Critics point out that FRBs show too much variation to be the product of a single, universal phenomenon like dark matter. Some repeat, others don't. Some come from young, turbulent galaxies, others from quiet corners of space. If dark matter is everywhere, why wouldn't these signals be more uniform? Then there's the practical hurdle. We've never directly detected any dark matter particle, making it hard to tie them to specific cosmic events. Yet the very impossibility of ruling it out is what keeps the idea alive. Science thrives on edge cases, the data points that don't fit. Dark matter's elusiveness means we can't yet dismiss its potential role in these signals. Every new FRB discovery adds another piece to the puzzle, and with telescopes like the Square Kilometre Array coming online, we're about to listen to the universe with unprecedented clarity. Whether these bursts turn out to be dark matter's calling card or just another cosmic quirk, one thing's certain: the universe is still playing coy, and the most thrilling chapters of this mystery may still be unwritten. In 2020, a signal unlike any other briefly crackled through the static of deep space, a radio pulse so peculiar it seemed to tick every box for an extraterrestrial transmission. Detected by Russia's Ratan 600 telescope, This narrowband burst originated from the direction of HD 164595, a Sun-like star 94 light-years away in the constellation Hercules. The frequency of the signal, 11 GHz, was eerily precise, far beyond what natural cosmic phenomena typically produce. To make matters even more intriguing, HD 164595 wasn't just any star. It was known to host at least one planet, a Neptune-sized world orbiting just inside the star's habitable zone. For a fleeting moment, it felt like we might have stumbled onto the real deal, a deliberate broadcast from another civilization. The excitement was palpable. If this signal was artificial, the implications were staggering. Calculations suggested that producing such a transmission would require energy on a scale humanity couldn't fathom, billions of times Earth's total power output. This wasn't just a whisper into the void, it would have been a cosmic shout designed to be heard across the galaxy. SETI researchers scrambled to train other telescopes on the star, hoping for a repeat performance. But the universe, as it often does, had other plans. The signal never returned. No matter how many times astronomers listened, the star remained stubbornly silent, leaving behind only a single enigmatic blip in the data. So what went wrong? The most likely explanation is also the most mundane: interference. Rattan 600's unique design, a ring of radio reflectors rather than a traditional dish, makes it exceptionally sensitive, but also prone to picking up terrestrial noise. Satellites, military radar, even stray signals bouncing off atmospheric layers can mimic the hallmarks of a cosmic transmission. Without repetition or corroboration from other observatories, the signal couldn't be confirmed as extraterrestrial. And in the world of SETI, one-off detections are almost always dead ends. But the Rattan 600 signal wasn't just another false alarm. It underscored a fundamental challenge in the search for extraterrestrial intelligence, the needle in a haystack problem. Our universe is drowning in radio noise, natural and human-made. Distinguishing a genuine cosmic signal from the background chatter requires more than just a lucky detection. It demands meticulous verification. Every candidate has to pass brutal scrutiny. Does it repeat? Does it match known astrophysical sources? Could it be explained by human technology? Most, like this one, crumble under the weight of those questions. Yet there's another lesson here, one that's easy to miss in the disappointment of a faded signal. The very fact that we can detect these whispers, that our telescopes are sensitive enough to pick up potential broadcasts from stars dozens of light-years away, is a testament to how far we've come. A century ago, we didn't even know other galaxies existed. Today, we're eavesdropping on the cosmos, listening for voices we may never fully understand. The Rattan 600 signal might have vanished, but the search didn't end there. It sharpened our methods, honed our skepticism, and reminded us that the greatest discoveries often begin with a single, tantalizing question echoing across the void, waiting for an answer. Among the countless radio whispers filling the cosmos, some stand out not for what they reveal, but for what they hide. Meet the odd radio circles, or ORC, enormous, ghostly rings of radio emission drifting through space with no visible source to explain them. These enigmatic structures stretch hundreds of thousands of light-years across larger than entire galaxies, yet when astronomers point optical telescopes at their locations, they find nothing. No stars, no dust, not even a trace of the superheated gas that usually accompanies such intense radio waves. It's as if the universe drew giant bullseyes in the sky and dared us to solve the riddle. The first ORC was spotted in 2019 by Australia's ASCAP radio telescope, a facility designed to map the universe in unprecedented detail. What made it so baffling wasn't just its size or its perfect circular symmetry, it was the sheer absence of anything that could be causing it. At first, researchers wondered if it might be a glitch, a smudge on the cosmic lens, but then more appeared. To date, fewer than a dozen ORCs have been confirmed, each one a spectral ring floating in the void like a cosmic smoke signal with no fire. The leading theories oscillate between the mundane and the mind-bending. One camp suggests these are shock waves from cataclysmic events, perhaps the aftermath of two supermassive black holes merging, sending ripples through intergalactic space. Others propose they're the remnants of starburst galaxies that burned through their gas so violently they left behind invisible bubbles of radio emission. Then there's the more exotic possibility. ORCs could be the fingerprints of entirely new physics, phenomena we've yet to theorize, let alone observe. What makes ORCs so revolutionary isn't just their mystery, it's how they're reshaping our cosmic toolkit. Traditional astronomy often starts with visible light, then uses other wavelengths to fill in the gaps. But ORCs flip that approach on its head. They're invisible in every spectrum except radio, forcing scientists to rethink how they map the universe. New telescopes like the Square Kilometre Array, set to come online in the next decade, promise to reveal hundreds more of these phantom rings, potentially unlocking patterns we can't yet see. The irony is delicious. In an era where we've photographed black holes and traced the web of dark matter, some of the most arresting cosmic structures turn out to be the ones we can't see at all. ORCs remind us that for every mystery we solve, the universe unveils another, sometimes in the form of a radio whisper so loud it echoes across the cosmos, yet so subtle it hides in plain sight. Rising from the heart of our galaxy like colossal hourglasses, the Fermi bubbles stretch 50,000 light-years across towering structures of gamma-ray energy so vast they dwarf the Milky Way itself. Discovered in 2010 by NASA, a Fermi gamma-ray space telescope, these twin lobes of searing radiation defy easy explanation. They're not signals in the traditional sense, but their very existence whispers of cataclysmic events buried deep in our galaxy's past, events powerful enough to leave scars visible across the cosmos. What could possibly forge structures this immense? One leading theory points to an ancient eruption from Sagittarius, a star, the supermassive black hole at our galaxy's core. Imagine a belch of cosmic proportions, a jet of energy erupting millions of years ago as the black hole devoured an enormous meal of gas and stars. The shock waves from that feast might have punched through the galaxy's gas layers, inflating these gargantuan bubbles like cosmic balloons. But here's the twist: the edges of the Fermi bubbles glow too sharply for such an old event. If they were fossils of a bygone eruption, time and turbulence should have blurred their boundaries. Yet they remain crisp, almost defiantly so, suggesting the energy that shaped them might still be coursing through the galaxy's veins. Then there's the starburst hypothesis, a different kind of violence altogether. Some astronomers argue these bubbles could be the aftermath of a frenzy of star formation near the galactic center, where hundreds of massive stars were born, lived fast, and died in supernova explosions. Their combined fury might have blown a titanic wind of charged particles outward, sculpting the bubbles over eons, but even this explanation falls short. The energy required would surpass anything observed in modern galaxies, making our Milky Way's past far wilder than we ever imagined. The most tantalizing clue lies in the bubble's composition. They're not just hot gas, they're crackling with high-energy cosmic rays, particles accelerated to nearly light speed. This suggests something far more exotic than a simple explosion. Could magnetic fields threading through the galaxy have acted as colossal particle accelerators, whipping matter to extreme energies? Or is there an unseen player at work, dark matter annihilations perhaps, or even relics of an intergalactic collision we've yet to uncover? What makes the Fermi bubbles so compelling isn't just their mystery, it's their scale. They're a reminder that our galaxy isn't some quiet backwater. It's a dynamic, sometimes violent place where energies beyond comprehension shape the cosmos. And while they may not be deliberate signals, their gamma-ray glow is a beacon, nonetheless, one that challenges us to piece together the Milky Way's explosive past. Every photon we detect from those towering structures is a message in a bottle, sent across millennia, waiting for us to decode its origins. If we listen closely, the Fermi bubbles might just reveal how galaxies live, breathe, and sometimes scream into the void. In 2017, astronomers tracking the fireworks of the cosmos stumbled upon something that defied all expectations: a brilliant X-ray flare in the spiral arms of NGC 6946, a galaxy nicknamed the Fireworks Galaxy for its frequent supernova. This wasn't just another stellar explosion. Over the span of just 10 days, the X-ray source flared to brightness 1,000,000 times greater than our Sun, then vanished without a trace. No gradual fade, no lingering remnant, just a cosmic light switch flicked on, then off. Supernova, the violent deaths of massive stars, usually leave behind some calling card: a neutron star, a black hole, or at least a glowing cloud of debris. But this nothing. It was as if the universe had staged a magic trick, and even the most powerful telescopes couldn't find the trapdoor, the leading theory. A failed supernova, a star massive enough to collapse under its own gravity but somehow skipping the explosive finale. Instead of lighting up the galaxy, it might have imploded directly into a black hole, swallowing its own death cry. The X-ray flare could have been the star's last gasp, a brief scream of matter torn apart at the event horizon before silence swallowed it whole. Then there's the black hole birth hypothesis. Picture a star not just dying but giving birth to something far stranger. As its core collapses, it could form a nascent black hole, still hungry, still chaotic. For a fleeting moment, that newborn singularity might devour nearby material with such ferocity that it unleashes an X-ray belch, a single, intense burst before settling into the darkness of its new existence. But the most tantalizing possibility, a star torn apart by an intermediate mass black hole, an elusive cosmic middleweight thought to lurk in some galaxies. Unlike the supermassive giants at galactic centers or the stellar mass black holes we've spotted, these mid-sized enigmas could rip apart a passing star in a way that produces a brief, dazzling flare, then nothing. What makes NGC 6946's X-ray mystery so haunting is its silence. Most cosmic explosions announce their presence with lingering echoes, expanding shockwaves, glowing remnants, or gravitational ripples. This one came and went like a shadow in the night, leaving behind only questions. Was it a star that forgot to explode, a black hole's first meal, or something even stranger, a phenomenon we haven't yet named? The universe, it seems, still holds its cards close, and every vanishing act like this reminds us just how much we have left to learn. The idea of a Dyson sphere, a colossal megastructure built around a star to harness its energy, sounds like pure science fiction. But what if we've already spotted hints of these engineering marvels in the cosmos? Meet the Dyson sphere candidates, stars that glow a little too brightly in infrared light, as if something massive and artificial is soaking up their energy and re-radiating it as heat. The first clues emerged in star catalogues, where astronomers noticed odd outliers, sun-like stars emitting far more infrared radiation than expected. One of the most famous, KIC 8462852 Tabby star, was just the beginning. Others, like TYC 3162911691, showed similar excess infrared signatures, sparking debates about whether we were glimpsing humanity's first evidence of advanced alien civilizations. Infrared excesses aren't inherently mysterious. Natural explanations abound. Thick disks of dust, swirling debris from planetary collisions, or even vast clouds of comets can all produce extra heat around stars. But the allure of the Dyson sphere hypothesis is irresistible. Imagine a civilization so advanced it constructs a vast swarm of energy-collecting satellites or even a solid shell encasing its star. The waste heat from such a structure would glow in infrared, exactly like the anomalies we've detected. It's a tantalizing thought, one that blurs the line between astrophysics and the wildest dreams of science fiction. Yet for all the excitement, skepticism remains the scientist's best tool. When researchers took a closer look at many of these infrared bright stars, they found simpler answers. TYC 3162911691, for instance, turned out to be surrounded by a thick ring of dust, not a megastructure. Even Tabby's star's strange behavior now leans toward cosmic dust clouds rather than alien engineering. But here's the catch: not every candidate has been fully explained. Some, like EPIC 249469361, still defy easy categorization, their infrared glows lingering in the realm of maybe. What keeps the Dyson sphere dream alive isn't just wishful thinking, it's the sheer scale of the universe. With billions of stars in our galaxy alone, the odds that at least one might host a civilization capable of such engineering can't be ruled out. And even if these candidates turn out to be dust clouds or debris, they've done something profound. They've taught us how to look. By scanning the skies for infrared anomalies, we've refined the search for extraterrestrial intelligence, shifting from radio waves to the language of heat and light. The real Dyson sphere might still be out there, hiding in plain sight, waiting for us to think bigger and look closer. Deep beneath the Antarctic ice, where sunlight never reaches, an array of sensors lies in wait, not for light or radio waves, but for the most elusive particles in the universe, neutrinos. These ghostly messengers, so insubstantial they pass through entire planets without a trace, occasionally collide with atoms in the ice, sending faint flashes detected by the Ice Cube Observatory. Most neutrinos come from harmless sources, the sun, cosmic rays, even bananas, but a few pack energies so extreme they can only be born in the universe's most violent events. And when scientists traced one such neutrino back to its origin in 2017, they found something astonishing: a blazar 4 billion light-years away, firing a jet of energy directly at Earth. Blazars are supermassive black holes at the cores of galaxies, but with a twist their jets point right at us, turning them into cosmic particle accelerators visible across the universe. The neutrino that slammed into Ice Cube matched the position and timing of a gamma-ray flare from blazar TXS 0506 plus 056, marking the first time a high-energy neutrino was linked to a specific astrophysical source. This wasn't just luck, it was a revelation. Neutrinos, long dismissed as useless ghosts because they barely interact with matter, suddenly became cosmic detectives, silent witnesses to the most energetic processes in existence. What makes these detections so thrilling is what they imply. Neutrinos don't just tell us where extreme events happen, they reveal how particles are accelerated to near light speeds. In the case of blazars, their jets likely hurl protons and other particles outward with such force that collisions produce neutrinos alongside gamma rays. It's a cascade of violence, a black hole's appetite powering a cosmic gun, with neutrinos as the smoking bullet. And Ice Cube's detection proved something even more profound. The universe's most energetic phenomena aren't just emitting light. They're broadcasting in a language we're only beginning to decipher. Yet for every answer, neutrinos bring new puzzles. In 2022, another ultra-high-energy neutrino struck Ice Cube, but this time no obvious source flared in coincidence. Was it a blazar too faint for our telescopes, a hidden cosmic catastrophe like a neutron star merger or a dark matter annihilation, or something entirely unknown? The absence of a counterpart is just as tantalizing as the blazar match. It hints at gaps in our maps of the sky, violent events lurking in the darkness, unseen until a ghostly particle whispers their existence. The hunt for neutrino sources is more than a scientific curiosity. It's a paradigm shift. For centuries, astronomy relied on light, visible, radio, X-ray. But neutrinos offer a new window, one that cuts through dust, gas, and even time. They're the ultimate cosmic messengers, unperturbed by magnetic fields or intervening matter, traveling billions of years undisturbed. Every high-energy neutrino caught is a postcard from the universe's most extreme addresses, stamped with the fingerprints of physics pushed to its limits. And as detectors grow more sensitive, we're on the verge of an era where these ghostly signals might illuminate the darkest corners of the cosmos, revealing engines of destruction and creation we've yet to imagine. The universe isn't just filled with the occasional burst of energy or flickering starlit hums. A constant, low-frequency vibration permeates everything, so subtle we barely notice it. But what if this cosmic background hum isn't just static? What if it's a fingerprint of the most mysterious force in existence, dark energy? Dark energy makes up 68% of the universe, driving its accelerating expansion. Yet we know almost nothing about it. It doesn't interact with light or matter. It doesn't clump or cluster. It's a ghost detectable only by its effect on the cosmos's stretching fabric. But some theorists suspect we might be listening for it all wrong. Instead of chasing shadows in telescope data, they propose tuning into the universe's hidden frequencies, those faint, omnipresent signals we've dismissed as noise. Here's the radical idea: certain ultra-low-frequency radio waves, those drifting between galaxies like cosmic whispers, could carry dark energy's signature. Picture space itself as a vast, vibrating membrane. Dark energy, constantly pushing outward, might create ripples in that membrane, ripples so slow they'd manifest as barely detectable hums in radio surveys. It's not unlike how seismic waves reveal Earth's hidden layers, except here, the tremors aren't from rocks shifting, but from space-time itself stretching under dark energy's relentless push. Critics argue this is speculative at best, a cosmic Rorschach test where we're projecting dark energy onto mundane background static. After all, the universe crackles with natural radio noise, dying stars, spinning pulsars, even the afterglow of the Big Bang. Isolating a hypothetical dark energy hum from that cacophony is like trying to hear a single violin in a stadium full of roaring crowds. Yet supporters counter that absence of evidence isn't evidence of absence. A century ago, cosmic microwave background radiation was just meaningless static until it revolutionized our understanding of the universe's birth. Could today's radio hum hold the same potential? The stakes couldn't be higher. If we could trace this hum to dark energy, it would crack open one of physics' greatest mysteries. We might finally understand why the universe's expansion is speeding up, or whether dark energy evolves over time, which could determine the cosmos's ultimate fate. Will it tear itself apart, collapse back into a singularity, or settle into some unchanging equilibrium? The answers might be hiding in those faint vibrations, waiting for the right instruments, the right algorithms, the right minds to decode them. For now, the cosmic hum remains a tantalizing what-if. But history favors the curious. Every major discovery began as a hunch, a whisper in the data that someone dared to chase. Whether this signal leads us to dark energy or down another path entirely, one thing's certain: the universe is always speaking. The real question is whether we're listening closely enough. For decades, cosmologists have faced a puzzle so confounding, they call it the missing baryon problem. Here's the mystery: when we tally up all the ordinary matter, the protons, neutrons, and electrons that make up stars, planets, and us, the numbers don't add up. About half of it is simply gone. Not dark matter, not some exotic particle, but the very stuff we're made of. It's like weighing a suitcase, knowing exactly what you packed, and finding it suspiciously light at the airport. The universe, it seems, has misplaced an unfathomable amount of itself. But what if the answer has been hiding in plain sight, woven into the fabric of space itself? Enter the cosmic web, a vast, intricate network of filaments stretching across the universe, where galaxies cluster like beads on a string. Theorists suspect the missing baryons are here, hiding as diffuse, superheated gas too faint to see with traditional telescopes. This isn't just any gas. It's a plasma so scorching it glows in X-rays, but so thinly spread it's nearly invisible. Like steam from a boiling kettle, it's there, just devilishly hard to spot. That's where unexplained radio signals come in. Some distortions in radio waves, subtle shifts in their frequency and strength as they travel through space, might be the key to mapping this elusive material. Picture a flashlight beam passing through fog. The way the light scatters reveals the fog's density. Similarly, as radio waves from distant quasars traverse the cosmic web, they pick up tiny fingerprints from these hidden baryons. The distortions are minuscule, but with sensitive enough instruments, they could trace the universe's missing skeleton. Recent breakthroughs are turning theory into reality. The low-frequency array in Europe and the upcoming square-kilometer array are tuning into these whispers, sifting through radio static for patterns that betray the baryon's presence. Early data suggests filaments of warm hot gas, exactly where models predicted, though still too faint to account for all the missing matter. The hunt is now a race to refine the signals, to distinguish cosmic fog from instrument noise, and to finally balance the universe's ledger. What's at stake goes beyond solving a cosmic accounting error. These baryons aren't just hiding, they're part of the universe's circulatory system, cycling material between galaxies and fueling star formation. Finding them would complete our picture of how the cosmos builds and recycles itself. And if the signals lead us to them, it'll prove something even more profound. Sometimes the universe's greatest secrets aren't written in light or shadow, but in the silent echoes of radio waves waiting for us to listen. Black holes have always been the universe's ultimate locked doors, regions where gravity is so strong, not even light can escape. But what if there's a crack in that door? A whisper slipping through. For decades, physicists have toyed with a wild idea. Tiny, quantum-scale black holes, no larger than an atom but packing the mass of a mountain. Unlike their colossal cousins, these hypothetical specks of cosmic might could evaporate in a flash, vanishing in a burst of energy so peculiar, it might just leave a signal we could catch. And if they exist, they wouldn't just fade quietly, they'd scream. Theoretically, quantum black holes could emit something called Hawking radiation, a faint glow of particles leaking away from their event horizons, slowly draining their energy until they pop out of existence. But here's where it gets eerie. If these micro-black holes are born from conditions we can't yet replicate, like the early universe's chaos or high-energy particle collisions, their death throes might produce bursts of gamma rays or even radio waves unlike anything we've seen. Imagine a flicker of energy, a blip on a telescope's readout, so brief and bright it defies all known astrophysical sources. That's the tantalizing possibility, a signal from the edge of quantum gravity, a realm where Einstein's relativity and quantum mechanics collide. Then there's the wormhole twist. If quantum black holes could theoretically form tunnels through space-time wormholes, their signals might be even stranger. Picture a pulse of energy that doesn't just fade but oscillates, as if echoing through a hidden corridor of the universe. Some models suggest these wormholes could produce resonant frequencies, like a cosmic tuning fork vibrating at specific pitches. Detect that, and you're not just hearing a black hole's death rattle. You're catching a glimpse of a bridge between dimensions. Of course, this is all speculative. No quantum black holes or wormholes have ever been confirmed. The energies required to create them are far beyond our current technology, and the signals they'd produce are buried in a universe already crackling with gamma-ray bursts, pulsars, and who knows what else. But that's the thrill of the hunt. Every unexplained blip in the data, every anomalous burst that doesn't fit the pattern could, in theory, be a signpost to these quantum enigmas. The search isn't just about proving sci-fi right. It's about probing the limits of physics itself. If we ever detect a signal matching these predictions, it wouldn't just mean quantum black holes are real. It would rewrite our understanding of reality, revealing a universe far stranger, far more interconnected than we ever dared to dream. Until then, we keep listening because the cosmos has a habit of surprising us when we least expect it. Most stars go out with a bang, one spectacular supernova explosion before fading into oblivion. But IPTF-14 HLS didn't just explode once, it did it again. And again, over the course of 2 years, this so-called zombie star erupted at least 5 times, brightening and dimming like a cosmic strobe light, defying every known law of stellar death. When astronomers first spotted it in 2014, they assumed it was a typical supernova until it refused to die. Instead of fading after 100 days like every other supernova on record, it roared back to life, shining brighter than it had before. It was as if the star had a reset button, collapsing and reigniting in a cycle that shouldn't exist. What could possibly fuel such bizarre behavior? The leading theory involves a phenomenon called pair instability supernova, where a star so massive, at least 95 times heavier than our Sun, becomes unstable in its core. Under normal circumstances, such stars implode into black holes, but IPTF-14 HLS might have skirted the edge of destruction, its core temperatures sparking runaway reactions that blew off its outer layers while leaving the star itself intact. Think of it as a stellar volcano erupting in stages instead of one catastrophic blast. The result, a supernova that refuses to quit, pumping out strange signals with each resurrection. Yet even this explanation doesn't quite fit. IPTF-14 HLS released 10 times more energy than a pair instability event should produce, and its light curves graphs of its brightness over time don't match any known model. Some researchers speculate it might have been a magnetar in disguise, its furious magnetic fields twisting the explosion into something unrecognizable. Others wonder if it swallowed a companion star mid-collapse, creating chaotic feedback loops of energy. Whatever the cause, one thing's clear: this zombie star is rewriting the rules, proving that even stellar death isn't as predictable as we thought. The implications ripple far beyond a single cosmic oddity. If stars like IPTF-14 HLS can explode multiple times, they might be responsible for unexplained signals we've dismissed as glitches or noise. Imagine a supernova's shockwave slamming into earlier ejecta, creating secondary bursts of radio waves or X-rays. Or consider the light echoes, delayed reflections of the explosion off interstellar dust that could masquerade as repeat signals. Suddenly, anomalies in old telescope data take on new meaning. What if some one-off detections were actually zombies in disguise, their true nature hidden because nobody thought to look for a star that refuses to stay dead? IPTF-14 HLS isn't alone. Other supernova survivors, like SN 2012Z, have shown similar stubbornness, lingering far longer than their peers. Each one forces us to reconsider what's possible in the universe's most violent acts. They're not just curiosities, they're keys to unlocking new physics, hinting at processes we've yet to imagine. And as telescopes grow more sensitive, we might soon find that zombie stars aren't the exception. They're a whole new class of cosmic phenomena, lurking in plain sight, waiting to upend our understanding of how stars live, die, and sometimes refuse to go quietly. Picture a civilization spanning multiple star systems, their ships threading between worlds like ancient mariners navigating by starlight, except their compass isn't magnetic. It's radio waves. This is the essence of the galactic GPS hypothesis. The idea that some of the universe's unexplained signals might not be messages or accidents, but cosmic lighthouses, purpose-built to guide travelers across the interstellar void. It's a concept that dances on the edge of science and speculation, blending the rigor of astrophysics with the thrill of imagining how an advanced society might solve a problem as practical as getting from point A to point B in a galaxy that's overwhelmingly, unimaginably vast. The premise isn't as far-fetched as it sounds. Human history is littered with examples of navigation systems tied to the heavens. Polynesian voyagers used the stars to chart paths across the Pacific. Early astronomers tracked Jupiter's moons to measure longitude. Even today, our GPS satellites rely on precisely timed radio pulses to triangulate positions on Earth. Scale that up to a galactic level, and the idea of beacons' narrow, powerful signals emitted at predictable intervals from known coordinates starts to feel almost inevitable. A civilization capable of interstellar travel would need reference points, markers to orient themselves in three-dimensional space where conventional maps fail. And what better way to broadcast those markers than with bursts of energy bright enough to pierce the cosmic dark? Of course, nature has its own version of this idea. Pulsars, spinning neutron stars that beam radio waves like cosmic metronomes, were once nicknamed LGM little green men for their artificial seeming regularity. Their pulses are so precise they rival atomic clocks, leading NASA to include pulsar maps on the Pioneer plaques and Voyager records as a way to triangulate Earth's location. If humans use dead stars as signposts, why wouldn't others? The difference, proponents argue, lies in the details. A deliberately engineered beacon might encode additional data, distance markers, directional cues, or even identifiers superimposed on the signal like layers on a map. Some FRBs' fast radio bursts show subtle frequency drifts or polarization patterns that, if not for the staggering energies involved, could almost pass as deliberate modulation. Yet for every tantalizing what-if, there's a sobering or maybe. Magnetars, for instance, produce bursts with complex substructure that mimic the very patterns an alien beacon might encode. Plasma physics in extreme magnetic fields can twist radio waves into shapes that look engineered to the untrained eye. And let's not forget Occam's razor. The universe is under no obligation to make its mysteries convenient for human storytelling. The most exotic signals usually trace back to the least exotic explanations: colliding stars, vibrating magnetic fields, or good old-fashioned telescope glitches. But here's where the galactic GPS idea shines brightest, not as a definitive answer, but as a thought experiment that stretches our perspective. Imagine a future where humanity's own probes, adrift between stars, rely on networks of orbiting transmitters to find their way home. Now rewind the clock 1,000,000 years and picture another species doing the same. The universe is ancient. The ingredients for technology aren't unique to Earth. If even one civilization cracked interstellar travel, their legacy might still linger in the echoes of signals we're only beginning to detect. Whether these cosmic breadcrumbs are real or just poetic license, they serve a deeper purpose, reminding us that the universe is stranger than we can suppose, and that every unexplained signal is an invitation not just to analyze but to wonder. After all, the line between a natural marvel and an alien artifact might just be a matter of who's listening and how boldly they dare to interpret the static. Among all the whispers and echoes of the cosmos, none is more profound than the faint glow of the cosmic microwave background, the CMB. This is the universe's baby picture, captured when it was just 380,000 years old, a snapshot of primordial light released when the first atoms formed and space became transparent. Stretching across the entire sky, this afterglow of the Big Bang is the closest thing we have to a universal signal, a message from the dawn of time itself. But here's the twist: the CMB isn't as uniform as it should be. According to the standard model of cosmology, the early universe was a hot, dense soup of particles expanding rapidly in all directions. The radiation left behind ought to be smooth, like the static on an old television screen. Instead, it's full of oddities, patterns that defy expectations. Take the so-called axis of evil, a bizarre alignment of fluctuations in the CMB that seem to trace a preferred direction across the cosmos. It's as if the universe has a hidden spine, a cosmic tilt that shouldn't exist if space expanded equally in all directions. Then there's the cold spot, a sprawling region in the southern sky where the CMB's temperature dips more than expected, like a bruise on the fabric of reality. Some theories suggest it's the imprint of a collision with another universe, a bubble beyond our own brushing against space-time. Others argue it's just a statistical fluke, a cosmic mirage in the data. But the more we study these anomalies, the harder they are to dismiss. What makes these patterns so unsettling is what they imply. If the CMB isn't as random as we thought, our entire understanding of cosmic beginnings might need rewriting. Perhaps the Big Bang wasn't the true beginning, just a transition from something even older. Maybe the universe is lopsided, shaped by forces we can't yet see. Almost tantalizing of all these wrinkles in the CMB could be echoes of a deeper structure, a fingerprint of dimensions beyond our own. The CMB's mysteries aren't just academic puzzles. They're the oldest signals we've ever detected, whispers from the edge of time itself. And unlike fleeting radio bursts or vanishing stars, they're always there, imprinted on the sky, waiting for us to decode their secrets. Every anomaly we uncover is a clue not just about how the universe began, but about what might lie beyond the limits of our perception. In the grand search for cosmic meaning, the CMB is both map and riddle, a reminder that even the faintest glow can hold the universe's deepest truth. From the electrifying wow signal to the ghostly whispers of dark matter, these 25 cosmic enigmas aren't just anomalies. They're windows into a universe far stranger than we ever imagined. Each one peels back another layer of the cosmos, revealing how much we still don't know. Take those bizarre odd radio circles stretching across galaxies with no visible source, or the Fermi bubbles, towering over the Milky Way like silent monuments to some ancient cataclysm. Even the humble neutrino, that ghostly particle from a blazar's jet, reminds us that the universe speaks in more languages than light alone. Then there are the signals that flirt with the extraordinary Tabbys, stars' erratic flickers, the repeating FRBs pulsing like cosmic lighthouses, or that fleeting whisper from Proxima Centauri that had us all holding our breath. Whether natural or just maybe something more, they challenge us to rethink what's possible. The zombie star IPTF-14 HLS died over and over, defying every textbook, while Oumuamua accelerated away as if pushed by unseen hands. Even the cosmic microwave background, that ancient echo of the Big Bang, hides wrinkles and cold spots that whisper of realms beyond our own. What ties these mysteries together isn't just their strangeness, it's how they transform our place in the cosmos. Every unexplained signal is a humbling reminder. We're newcomers in an old, vast universe, still learning to decode its vocabulary. Some answers may come tomorrow with a breakthrough observation. Others might linger for centuries, taunting our curiosity. But that's the thrill of the hunt. The universe isn't just hiding its secrets, it's dangling them just out of reach, inviting us to look closer, listen harder, and imagine bigger. So stay curious, follow those flickers in the data, the anomalies that don't fit, because whether these signals are cosmic accidents, undiscovered physics, or even, dare we hope, messages from afar, they prove one thing: the universe is anything but silent. It's a symphony of mysteries, and we've only just begun to hear the opening notes. What's your favorite cosmic enigma? Drop it in the comments, and don't forget to like, subscribe, and join us as we keep exploring the universe's greatest unsolved whispers. Who knows, the next big discovery might be just one signal away.